Welcome back to ECE 320A. We have our exam a week from Thursday. This is a Tuesday, so you have about 10 days before our next exam. You'll have 2 homework assignments prior to that. You have 1 homework assignment due this evening. And to help you with that are the Unit 7 supplements on convolution. Flip and slide, intervals and limits, those are designed to help you figure out what you want to do relative to performing convolution, and then there's a couple of examples of doing convolution. The exam again is Thursday, and today what I want to talk about is the next unit beyond convolution, which is transfer functions and how you use them. We can motivate transfer functions by looking at a little bit of elementary filter design. How do we design a filter? We'll get more of that in Unit 10, but we can at least start to think about that now. Then we'll say, okay, now that we have these transfer functions, how do we use them? And we'll be able to look at how do we find a system response. How do we look at the S-plane diagram, the poles and the zeros? Can we now use that information of a transfer function to find a sinusoidal steady state response very quickly by just analyzing the transfer function or by working with the transfer function and not having to inverse Laplace transform every piece of your partial fraction expansion? And then we will look at a way to graphically determine this expression of interest, which is h of j omega. It's the transfer function evaluated on the imaginary axis at a particular omega value, where that omega value is consistent with the sinusoid that you're exciting your system with. So keep all of these frequencies in mind, these ideas in mind, or this list of topics, and that's where we're trying to go for today and beyond. Transfer functions of circuits. This is the block diagram description, and many subsequent classes are going to use this. Now you may have multiple subsystems as blocks, and you may interconnect these. It might be helpful if you're building up some MATLAB code or something. And now what you want to do is figure out what happens at the output if you're given a particular system. Today, that system for us will be filters. We'll derive h of s's, transfer functions, for different kinds of filters. What happens when we hit that filter with an input? What do we see at the output? We know we can do that in 2 different domains, either the kitchen or the living room. We can do it in the frequency domain. That's how a lot of times you like to do it, because now you're simply multiplying together these 2 transformed quantities. The Laplace transform of your input, and h of s is this transfer function. How many transfer functions are there for a given circuit? There can be many, right? So when you're given a circuit, don't just think that there's one transfer function associated with that circuit. It depends on how you've selected an output variable in that circuit. It could be a voltage, it could be a current, it could be different voltages and currents throughout that circuit, and you might be exciting it in the same place, and then that will actually produce a different output. In the frequency domain, it's this multiplication. In the time domain, it's convolution. And that's what you're learning now. And the reason you're learning it now is sometimes this x of t waveform that you're given might not look like something that you could find in a table and find a Laplace transform for. And for that reason, then, we find the impulse response of our circuit, h of t, which is the inverse Laplace transform of the transfer function, capital H. we convolve it with x of t to generate the output y. That's how we find y of t in the time domain. We can also find y of t in the time domain from capital Y of s in the frequency domain by inverse Laplace transforming. That's why we need these skills of Laplace transforms and inverse Laplace transforms. It's very useful. You may want to be working with products of transformed expressions. Let's look at some examples. The first one that we will look at, I think we've talked about this over and over and over again. A low-pass filter, an RC. Now if somebody gives this to you in an interview, you have this cold. You can do this in your sleep. They say, can you provide a circuit that will produce a low-pass filter? And this particular low-pass filter is passive because it's just made up of resistors and capacitors and inductors. We don't have to energize any of the systems in this circuit to make it work, to make it operate. It's passive. You just have to get a resistor and capacitor from the lab, put it together in this manner, and you have a low-pass filter if you call the output this voltage across your capacitor, and the input is the input across the series connection of your resistor and capacitor. In the frequency domain, we can then replace those parameter values with their impedances. R goes directly over to R in the frequency domain. The capacitor has an impedance of 1 over SC. If we're interested in transfer function, we don't have to worry about initial conditions. We can now simply look at this circuit and say, oh, I have two impedances. One up top horizontal and one vertical, Z1 and Z2. Now I have voltage divider Z2 divided by Z1 plus Z2. Or 1 over SC is the impedance that Y of S sees. And the total impedance is R plus 1 over SC. We can then obtain just a ratio of polynomials of S by putting everything over in the numerator a common denominator of SC and in the denominator a common denominator of SC. Those cancel and we're left with 1 over S RC plus 1. With that 1 as our constant, it being normalized, this is now in time constant form. And the time constant tau is this RC product. If somebody said, oh, what's the time constant of this first order, it has one energy storage device, low-pass filter, you can say it's the product of R and C after deriving this transfer function. And what does that time constant provide us with in terms of insight? If I give you a time constant, what do you now know about that particular circuit? What do you know about the transient behavior? You know how long you're going to have to wait for the transient to disappear. If you're exciting this circuit with something that continues for a long period of time, you're going to now have to wait 5 time constants before the transients are gone and you're in a steady state operation. That steady state could be a constant steady state, or it could be a sinusoidal steady state. We use steady state to refer to both. We can now look at a different circuit. This is now an active. Active because we have an op-amp, and what's maybe confusing when you first look at this is the fact that you don't see the power supplies that are being applied to that op amp. But this op amp has to be energized in order for this circuit to work. You have to supply it with some DC voltages at the appropriate pins on this op amp to make it functional. It's now an active device. And there's a couple of other things going on here just by the way it's configured. We are now actually applying feedback in this circuit. We're measuring the output voltage V sub 0 and we're feeding that back through this feedback resistor R sub F, and we're connecting it to the inverting terminal. That's now negative feedback. If we have V sub 0 getting big, now that gets applied as like a negative at the input, so it's kind of moving in the opposite direction to how you're applying the input, or how the input is affecting the output. Negative feedback allows us now to essentially assume, if we're in linear operation, these two pins at the inputs of your op amp are effectively at the same value. They're virtually shorted. You have V sub P, I'm saying P for positive input terminal, and N for negative or inverting terminal. Those two voltages are effectively equal when we have this negative feedback configuration. And from this diagram, we obtain this transfer function. And what does this transfer function tell us? It's an inverter, isn't it? It's negating what we put in at the input. This now tells us if we put in something at the input voltage side, we flip the sign, and is there any memory or is there any transient behavior in this particular circuit? If I wiggle the input, when will I see something wiggling at the output? Instantly, right? This is just a scale change. This is just an inverter. And if you wanted it to be a buffer between different stages of some circuit, you could make these two resistors the same size. Being the same size would now say, oh, all this is an inverter. The magnitude stays the same. You can also adjust the magnitude by these ratios of the feedback resistor and the input resistor. I anticipated you maybe put on your cap, your questioning hat, and you said, how did this happen? How did you derive this relationship or this transfer function for that particular circuit? So the answer to my question, or to answer this how, is one way to analyze this would be to perform KCL or nodal analysis at a node of interest. And the node of interest is actually that inverting terminal node. If we now look at KCL here, what do we have? We actually have this current, let me call that I1, coming into that node. We have this current, I sub F, and then we have this current, let's say, going out. Let's call this one I sub 0. And because of this op amp, the impedance is so large at that inverting terminal and at the non-inverting terminal that we don't have any current flowing into those terminals. I sub 0 is 0. But in this particular labeling, do you see that KCL says I1 plus I sub F, those are coming in, equal what's going out, which is I0. That's what we have. And you just said because of the high impedance of at the inverting terminal, we can say that there's no current going in to that op-amp circuit, and now the sum of those two currents at that node have to sum to 0. And how do we define, did I say I sub 1 or I sub I? Let me change this to I sub I. What is that? What is I sub I? Theoretically, it's capital V sub I. It's the voltage dropped across R1 divided by R1. And the voltage dropped across R1 from left to right, the way that we've labeled I sub I, is VI minus V sub N. But what's V sub N? Well, since we are assuming, since we know with this negative feedback that those two terminals at the input of the op-amp are equal, and we've grounded the 1, we don't need to worry about that. That's at 0. So now we have V sub I minus 0, or just V sub I, divided by R sub 1 is I sub I. What is I sub F? Now it's the voltage dropped across that feedback resistor, which the way that we've labeled I sub F, it's V sub 0 minus V sub N, and we know what to do with V sub N, divided by R sub F. We now have it. We now know that this expression gives rise to V sub I over R1, that's V sub I, plus V sub 0 over R sub F, and that's equal to 0. If we multiply all terms by R sub F, which we can do, and put this V sub I term on the other side of the equality sign, or subtract that term from both sides, we end up with and that's what we were trying to show. We now have, if we divided both sides by V sub I, we would have our transfer function, which is this inverter circuit. It's not hard to replay that derivation if you forget it, or forget this formula. Let's now step it up a notch and look at another filter. This is now a low-pass filter. It's active because we have an op-amp that we have to supply power to. We have to energize it. Oh, we've done just a little different. Something just a little different. We've now put a capacitor in parallel with that feedback resistor that we had before in the inverting circuit. Now we've put some energy storage device around this op-amp. But we can still think of this in the same way that we had thought of the previous inverting circuit. And again, we have negative feedback. We're feeding back a signal from the output to the inverting terminal of the op-amp circuit, and that gives us now this negative feedback that is desirable. We want that to be in place. And the way that we can solve this is simply to look at the impedances that are interconnected around this circuit as generalized resistors that we already analyzed in our inverter circuit. Meaning we have an input impedance, that's right here, and we have a feedback impedance right there. Well, the input impedance is trivial since it's the same as what we had before. Let's now focus on this feedback impedance. This is now our Z sub f. This could be thought of as a Z sub I. Hopefully you can see that that impedance Z sub f is just a parallel combination of two parameters or two impedances. Z sub f is now equal to R sub f in parallel with the impedance of that capacitor, 1 over SC. And if you remember the formula for combining two parallel resistors, you can just generalize that to impedances. We have the product divided by their sum. And if you put both numerator and denominator over the same common denominator of SC, those denominators cancel, and you're left now with R sub f over S R sub fc plus 1. And in terms of Z sub f and Z sub I, do you see that the transfer function is what we would expect it to be? If we now wanted to know what's this transfer function between the input, did I call it V sub I? Yes, I did. Between V sub I and V sub O, that's just like what we had in the inverter circuit if we said, oh, instead of the feedback resistor, we have our feedback impedance that we were calling Z sub f, and it's a function of S now, and we have our Z sub I of S. That we could derive just putting in blocks Z sub I and Z sub f and rederive what we just did for the inverter. And now we need to simply plug in the appropriate expressions for those impedances. And now you can see how you can go home now and play with this and say, oh, let me make Z sub I a little different than just a resistor. Oh, let me make Z sub f something different than what he did in class. Let me do it a series combination, for example, and see what happens. What kind of circuit do you build or filter do you build? In this case, we now have minus, and I'm going to do this, well, this is now R sub f over, you could do it several different ways. Let me do it in a not so quickly. That R sub 1 can go up into the numerator of R sub f. It's now R sub f over R sub 1. And I can just drop the denominator down so that my transfer function is now minus R sub f over R1 over S R sub fc plus 1. And this is now our third transfer function, h sub 3 of s. H sub 3 of s is now minus R sub f over R sub 1 over S R sub fc plus 1. And we said that this was supposed to be a low-pass filter. How do we justify that or convince ourselves that that's the case? What's the DC gain of this transfer function? What is DC in terms of S? S is 0. Now if we can find or evaluate this when S is equal to 0, that will be our DC gain. We plug in 0 for S and the denominator now just becomes 1. Or we now have our DC gain is now this minus r sub f over r sub 1. Where's our pole? Or do we have poles and zeros in this transfer function? We have no finite zeros, do we? There's no s in the numerator. We do have a pole. And that pole is the value of s that causes that denominator to vanish or to equal 1. I'm sorry, to equal 0. We set that denominator equal to 0 and solve for s, and that's where our pole is located. Or we have now a pole at s equal to minus 1 over r sub fc. We have a DC gain. Let's not worry so much about the minus sign. We have a DC gain of r sub f over r1. And then we end up with a pole at a frequency of 1 over r sub fc. In terms of a Bode plot or a frequency response, that pole tells us where we're going to start going down or rolling off that low-pass filter. Our break frequency is now, let's say that we'll just call that omega sub b, is 1 over r sub f c. That's where our pole is located. Or we can now quickly sketch, if we didn't have MATLAB available. We had a long discussion about the beauty of MATLAB before class, so I'm trying to plug it up, I guess, or enhance that discussion. This is what our low-pass filter looks like. How fast are we sloping once we start sloping? Do you remember what we said? This is now, if we were looking at this, this is our frequency axis, but it's actually the log of omega, and the log of omega allows us to put a lot of frequencies within a shorter width on our paper. And it makes the drawing easier. We have a dB scale. This is now the magnitude of h sub 3 of j omega in dB. And what is this? What's the magnitude there? That's our DC gain in decibels. So we take 20 log of that DC gain's magnitude, and that's where we are beginning. That's what this value is. This is 20 log base 10 of r sub f over r1. That's just a number. And when we get to our break frequency, that's what this is. And that was 1 over r sub f c. And now you can see how you could design this low-pass filter. If you want that low-pass filter to have a bandwidth of 100 radians per second, you would pick 1 over r sub fc, that product, to equal 100. If that's the bandwidth that you wanted. Getting back to my earlier question, now that we've reached the break and we start decreasing in this straight line approximation, do you remember how much I said we were going down? Every decade we went down so far. I said something per decade. Do you remember? How many dB did we drop per decade? And it kind of is somewhere on the screen a little bit. 20 dB per decade, didn't we? So each decade we're going down 20 dB. So this slope change is minus 20 dB per decade. Or if you didn't want, and decade is a factor of 10. That we know. If you said, okay, how many decades have elapsed? You know that's 10 years for each decade. So the decade being a factor of 10, that's not that unknown to us. But what's an octave in terms of a factor? If I said, okay, now sing the middle C, can't do it, neither can I. I was hoping somebody could help me. But now you sing middle C, and I say sing the middle C one octave higher. What's the change, or what's the factor in frequency between those? An octave is a factor of 2 in frequency change. So when I say an octave, I'm now saying a factor of 2 in terms of frequencies. So this is now a factor of 2. The slope then is minus 20 dB per decade, or it's minus 6 dB per octave. So if you didn't want to go quite as far, you don't go down as far. So if you just needed to go a factor of 2, an octave higher in frequency, and then see where you're at, now you would be dropping down at minus 6 dB per octave. That's for each single factor, and we only had one pole factor in that low-pass filter. We had a first-order low-pass filter, and that's why we're dropping at 20 dB per decade or 6 dB per octave. So now the question was, can I explain an octave being a factor of 2 versus a factor of 8? Maybe you're thinking of 8 notes in a scale, but if you looked at the frequencies, if you looked at playing those tones, you would actually see that typically one, now I'm drawing a blank, what's the A above middle C frequency-wise? Is it 440? So it's 440. Then the A an octave above that is 880. It's a factor of 2. Even though there are 8 notes, whole notes maybe, there's 12, I think, half steps. I'm not a musical theorist, but you get the idea, hopefully. It's really just a factor of 2 in frequency in an octave. Yes?
But how do you get in 6?
So now, if you now did this comparison or derivation, you could derive, oh, I have minus 20 in a factor of 10. Now if you measured that same slope over an octave interval, you would see, oh, it's actually sloping at minus 6 per octave. So you could graphically show that relationship if you wanted to. You could simply identify, oh, this value as in terms of a frequency is 4. Let me go to 8. Oh, I have to be 6 dB down if this is now 20 dB down. Let's say that this is now at minus 6 dB. Let's just, for argument's sake, that 20 log of RF over R1 is minus 6. And let's say that this break frequency was 100. Now if you go over here to 1,000, what's this point going to be? Why did I pick minus 6? Let me not do that, because now you're going to get it confused with minus 6 dB. Let's say this is minus 4. What would this dot be magnitude-wise in our straight line approximation? What would its value be? It's a decade beyond 100, and we said we're dropping 20 dB for every decade. That particular dot would be at minus 24. Let's say now somebody says, oh, let's go to 2,000 and see where we're at in terms of our magnitude. Where is 2,000? If this is 1,000, this is now 10,000. Where is 2,000? What's log of 2? It's 0.3. So you're 30% of the distance between 1,000 and 10,000 to get to 2,000. It's not chop this up into equal parts and that will be 2,000. It's a logarithmic scale. So right here, if I could draw it, this would now be 2 times 10 to the 3, or that's now 2,000. I come over here, and what's that? What's the value of the magnitude curve at that point? It's 6 dB down from minus 24. This must be minus 30. Do you see how you can resolve these values along that magnitude plot in finer pieces if you just step over an octave instead of a decade? This is now minus 30 dB. Just giving you something to sort of chew on before we get there after exam 3, which is how to actually sketch these straight line plots. But here I'm trying to illustrate that this blue curve is associated with this active low-pass filter.
So if that line was straight all the way, that meant that my circuit didn't have anything.
If what was straight?
If this was straight all the time.
So now if I was at minus 4 dB for all frequencies, is that what you're saying? Then I didn't have any kind of low pass characteristic. I would pass everything. That would just be an inverter circuit, wouldn't it? It would not be attenuating higher frequency content. Here we're attenuating signals that occur at 1,000 20 dB more than we're attenuating signals at 100. That's what we're saying with this particular sketch and these hypothetical values. But once I pick some values, now I can fill in the blanks. On an exam, if I said, oh, this point is minus 4 dB at 100, what is it at 1,000? When you know the break was at 100, you better be able to fill in the blank. That's filter number 3. Filter number 4. Let's see if we can create a high-pass filter that is in fact active. And now let's build it a little bit differently. But if you're now trying to envision what this looks like in terms of its frequency response, do you have a picture? If this is a high-pass filter, aren't you expecting something like that? This would be a high-pass shape for the frequency response. This would be H sub 4 in dB. Let's see if we can build one out of some op-amp circuits. Suppose that I now have an op-amp, same configuration that I had before in terms of the inverting terminal up top, the non-inverting down below, but now I'm going to put right here at the non-inverting terminal, I'm actually going to put an inductor to ground. Then I'm going to put a resistor here, and I'm going to apply my input waveform right here. Let me call this V sub G of t. Right now, okay, but I would really like to have negative feedback so that this operates in a linear fashion, this op-amp circuit. Now I've just grounded that inverting node. Let me put in negative feedback. So that now this is my feedback resistor R sub F. And I hope you can see that we do have negative feedback, and here is my output. In that circuit. And did you do this? I heard you had op amps in 220. Did you do these designs in 220 with capacitors? Now I have an inductor, so I just twisted it a little, right? So now you're lost, but not really, right? Let's now, what do we know is true? Let me go ahead and label this a little bit. Let me label this as somebody's having a revolt. So we have V sub P here. I guess this circuit you're not comfortable with. Let's call this V sub N just so that we can have something to talk about. And let me call this I sub N and this I sub P. And what do we know about I sub P and I sub N? Those are 0. If I sub P is 0, it's like this little circuit can operate by itself, this sub-circuit. There's no current going into that op amp, so I can just analyze this like a series RL circuit. Yes? Somebody's still laughing about the revolt, I guess. I don't. So now let's examine. We're going to analyze this in stages. Let's examine this non-inverting terminal subcircuit, or examine the V sub P subcircuit. The reason we can do that is you just told me that the current going into that non-inverting terminal is 0, and now you can just think of this subcircuit in isolation. It is connected to that, so its voltage, whatever is at V sub P, will get applied to that non-inverting terminal, but there's no current flowing, so it's not loading this circuit, this subcircuit. Let's draw that little subcircuit. And then you'll be able to convince yourself how straightforward the analysis is. Here's our V sub P, and if we want, we could say, okay, that's there, which is consistent with the grounded terminals on that inductor. Here's our R1, and here is V sub G. How do we, now what we want to do is find a relationship between V sub G and V sub P, or a transfer function. And you can do that now. We simply can do a voltage divider again to find the transfer function between V sub G and V sub P. Doing that, V sub P of S, that voltage at the non-inverting terminal of the op amp, is now SL over R1 plus SL. That's the transfer function. And this now we're calling V sub G. If we wanted to, we could start reshuffling some of these coefficients so that we get this in time constant form or pole zero form so that we can feel more comfortable with what we have. Suppose we now factor out an R1 from the denominator. And let me move the S and the R1, or the linear term in S and the R1, let me just switch places with those. What do I now have multiplying S if I factored an R1 out of SL? And what do I have now in the constant term in the denominator if I factored out the R sub 1? Well, that looks kind of ugly with that R1 downstairs. Let's just push it upstairs in the denominator of our numerator. Or we now can rewrite this as S times L over R1, and downstairs we have S L over R1 plus 1. And that should start making us feel a little bit more comfortable. What is this term that scales S? What have we been calling that? Boy, we're poking the bear in different locations, aren't we? Let's see. Let me try pole. Let me see time constant, 0, frequency. What do we have? That was a multiple choice. How many choose frequency for L over R1? What is S? So now when you go home or you're in your interview and somebody says, what is S? What are you going to say? You're going to go, it's a complex frequency. Frequency, huh? So now we have a frequency times something giving us a dimensionless quantity. 1 is dimensionless. So something times a frequency, and frequency could be radians per second. It's per second. This is a second. That's a time. That's a time constant. That's what you should have been feeling comfortable or good about. Let's call this, since we're in the 4th circuit, let's call that tau sub 4, our 4th time constant. And this entire transfer function, is that pole zero form or time constant form? Can you explicitly see the pole? Well, you can, but you're doing some calisthenics or exercises in your mind, more so than it's just jumping out at you. You solved that for S to find your pole. But now it's in time constant form, isn't it? Because the constant has been normalized to 1. This is now our time constant form. What if we wanted to put it in pole zero form? Can we just factor that L over R1 out of the S term? And then it'll cancel with what's upstairs, and we have our pole explicitly visible in the denominator. Meaning, we can now say, oh, we could rewrite that. V sub P of S is equal to S over S plus, and now this is R1 over L V sub G of S. And let's call this, we're not done. We just analyzed a subcircuit of that overall circuit. We've just looked at the little subcircuit that's connected to the inverting terminal. I'm sorry, the non-inverting terminal, the P terminal. Let's call this H sub P for that reason. And this is in pole zero form. Do we have a finite zero? Do we have a finite value of S that causes the numerator to vanish? Yes. And it's at 0, isn't it? We have a 0 at 0. S. S equal to 0 will cause that numerator to vanish. Where's our pole? Minus R1 over L, isn't it? What's the DC value of this transfer function? 0. So if we looked at really low frequencies, we would have nothing for a gain. Meaning, the magnitude plot of this is coming up from the basement, and then so this upward slope is due to a 0 factor, and we had a 0 at the origin. And how fast are we coming up? We have one factor that we're coming up from the basement or the bottom from, and what's our slope when we just have a one linear factor? What's that magic number? One of the magic numbers. Let's do it in decades. It's plus 20 dB per decade. So this is now going up at plus 20 dB per decade. And where did this break happen? We're going up, and then we hit a pole, and the pole contributes a slope down. We're going up at 20 dB. The pole gives us a slope down of minus 20 dB. What's our actual slope? They cancel each other out, so now we're flat. And this break occurs at the break frequency, omega sub b, which from the pole pole 0 form is now this R1 over L. Now, we're partway home. We've just looked at this little piece. We now need to look at the other piece. And how can we solve or look at or examine what's happening at the inverting terminal? Could we do our KCL or nodal analysis? What do we know? Well, we don't know what Vn is, but we can solve for it. And what if we want to know, well, which way do we want? Suppose we want this current going from right to left through R sub 2. That's just V sub n over R sub 2. What about if we wanted the current let's call this I sub f, and let's call this one I sub 1. I sub 1 is Vn over, or Vn minus 0 divided by R2, right? So now if we do KCL, we now have V sub n minus 0 over R sub 2 plus I sub f. What's that one look like? Vn minus Vo over R sub f. And those equal 0. We can now find a transfer function between Vn and Vo. Let's combine the terms that scale V sub n. I have a 1 over R sub 2, and I have a plus 1 over R sub f. And if I put the V0 term on the other side, what do I have on the other side? If I add V0 over R sub f, I don't have anything on the left, and I have what that was on the right. I can clean this up by multiplying every term by R sub f. Then I just have v sub 0 by itself. I don't know why. I'm just trying to keep you on your toes. Some of you are on the other side of the toes, on your pillow with your head. But v sub 0 now is on the left. And I've now multiplied everything by r sub f. What do I have that scales v sub n? I have r sub f over r sub 2 plus 1. There's another transfer function between v sub n and v sub 0. Let me call this h sub n, since it was associated with the inverting terminal of that subcircuit. Now let's try to find the total transfer function between v sub g and v sub 0. We want to know if I wiggle this, v sub g, what happens at v sub 0. And let's start with the output side. We have an equation for v sub 0. We just derived it here. We have v sub 0 of s is equal to h sub n of s times v sub n of s. Oh, but now we're cooking now. How are v sub n and v sub p related? They're equal, aren't they? Because we have negative feedback and they're operating in this linear operating region. So now anywhere I had a v sub p or a v sub n, I could replace it with the other one. I had v sub n, let me replace it with v sub p. They're the same. There's v sub n. Let me replace that with v sub p. But I had a way of relating v sub p and v sub g in the original subcircuit, didn't I? Don't I have v sub p is h sub p v sub g? Let me replace v sub p then with h sub p v sub g. So that now I have h sub n of s times h sub p of s v sub g of s. Oh, are you guys as excited as I am? Do you see what we have? We have a product of two transfer functions giving us the total transfer function between our input, v sub g, and our output, v sub 0. Isn't that amazing? This is now what we will call our fourth circuit's transfer function. And if we just multiply those together, we had this. That's just a scaling. That's just a number. So that can go in the numerator of what h sub p was, and h sub p was this. All I'm going to do now is put in the numerator that scaling function that I had before. Or I now can say that 8 or v, why did I, somebody else is sleeping. This was h sub 4, not v sub 4. This was h sub 4. And now we have v sub 0 of s is that combination. It's r times r sub f over r sub 2 plus 1. That was the scaling factor. S plus r1 over L. And what do we have for a shape? What's this transfer function? This is now our h sub 4. At low frequencies, what does this give us? If I shake this really slow, or with a constant, what are we going to see at the output? 0, right? Because you have a 0 at DC. You have a 0 at the origin, at 0. So this has no gain at DC. At low frequency, you're not hearing much. Then we're coming up, because that's a linear factor, we're coming up how fast? 20 dB per decade. And then what happens? Then we stumble into this pole, and it cancels that slope change that we were coming up, and those are supposed to be equal angles. We add them together, we're flat. This again is a, let me draw it and then you can answer. We're coming up from the bottom, then we have a break at, that was R1 over L. And what kind of a shape is that? Oh, and this was plus 20 dB per decade. If I gave you a multiple choice question, oh, we're back in 220. Well, we're doing op-amp circuits, for crying out loud. So now A is low pass, B is high pass, C is band pass, and D is band reject. What is this? Break. Is it? Oh. Oh, my head is hurting. You guys are playing with me. So break is B, right? B was high pass. This is high pass. I assume break meant B for your, A was apple, B was break, C was carrot, and D was, I don't know, donkey. Right? We got to kind of, why not? So, what is that filter? High pass. So this is now a high pass. What if I said, show me a band pass? What would you draw on a piece of paper if I said, draw me a band pass magnitude response of a filter? Band pass means you're passing a particular band of frequencies. We have debris in the air. We're passing it. I think it was a piece of cotton. Oh, it was it's a multiple choice question. One was mosquito, one was cotton, and one was a spider. What's D? An elephant. So now I want you to draw, I hope no one listens to this. I want you to draw a bandpass filter. What's it look like? You're passing a particular band of frequencies, so you want to not favor low. You don't want to favor high. Boy, I didn't do a very good job. Let's make it kind of symmetric with the slopes. This is now a band pass. It's really sort of a combination of a high pass with a low pass. We can put those together. What about a band reject? It's kind of the opposite of this, isn't it? So you might, depending on how sharply you reject those frequencies in that band, you might have something that looks like that. And this you could now say is a band reject. Yes?
So is the slope on those always going to be 20 decibels per decade?
Is the slope always 20 dB per decade? And the answer is no. It's going to depend on how big or what order of filter you have. If you had a second order filter, let's say it's low pass, then eventually at high frequencies you're going to be sloping at twice the minus 20 or minus 40. Do you see that you're going to be sharper now? You have a steeper slope. If it's third order, you're at minus 60 dB per decade. It depends on the amount of energy storage devices you have in your circuit. But for our first order pieces, each first order factor gives us a 20 dB per decade change. If it's upstairs in the numerator, you're sloping up. Those are zero factors. If you're downstairs in the denominator, those are poles, you're going down. Those give you negative slope. Let's now start talking about how we can use all of this. Now I've motivated this idea of systems. We have all these multiple choices, don't we? We have A, B, C, and D. B is a break, apparently. So we're not taking a break for a few more minutes. We want to now talk about systems and how they respond. So let's now look at response of systems and S-plane diagrams. S-plane diagrams are going to be poles and zeros. And I see that they followed through. Now they've put more tents on them all. Are they still there? See? All I have to do is ask for some poles and some zeros and we get tents. All right, so let's look at this. We have our time domain column, and we also have our frequency domain, or S domain. Suppose we start basic. What if we look at this passive low-pass filter? That was transfer function number 1. What did it look like in the S domain? What was its transfer function? What was H sub 1 of S? This was our passive in pole zero form, wasn't it like that? What's our DC gain? Plug in S equal to 0 and you get 1 over RC over 1 over RC, or 1. That looks good. And what are you doing at high frequencies? S gets really big. Oh, we're attenuating at high frequency. So this is low pass. If that's now our transfer function, what's the impulse response look like in the time domain? If I gave you that transfer function on the final and said, what is little h sub 1 of t, that should just be like piece of cake, right? What's the impulse response? What's your mode? Just deep breaths. Deep breaths. Don't throw anything. Don't kick any shins. We're closer now because we're working from a tighter screen. Yeah. Some of you guys, you won't sit on the first row next time, will you? This is a little bit too close. Space. What's H sub 1 of t? What's the mode? Do you see the mode? Are the doors closed? Now they're going to go, he's seeing modes in there. What are they studying? What's the mode of this?
1 over RC to the power negative 1 over RC.
Yes. So the mode, you gave me the answer, didn't you? You gave me the whole thing. But the mode is just a decaying exponential. It's a passive circuit. You would expect it to just be an exponential. And you know where the pole is. And you know the time constant. They're inversely related. The pole is at minus 1 over RC. That's in the exponent. And it's multiplied by t. It's now e to the minus t over tau, or tau is RC, or it's e to the minus 1 over RC times t. That's the mode, and we've actually scaled that by 1 over RC. Right? Thank you. I had to put the, because I broke one of these tips dropping it. I had to make sure, yeah, that was a, okay, where were we? Impulse response. We needed to get the impulse response. So now the impulse response is 1 over RC e to the minus 1 over RC t. That's the impulse response. Or we could write that in various ways to emphasize the fact that this is now our time constant. And suppose we put in some numbers just to give us something to think about. Suppose that I now said that h1 of t is equal to 10 e to the minus 10t. What am I assuming RC is equal to? What is tau? 0.1. We have 1 over 0.1 gives us 10, doesn't it? So RC is now 0.1. What's that good for? What does that time constant tell us? How long do we have to wait when we start shaking this before we can neglect the transient? You see all of this, these different pictures of people doing signals. I'm trying to give you a signal. I don't know how to do tau, but you have 5 tau, right? What's 5 tau in this case? 5 times 0.1. It's half a second. That's how long you have to wait before you no longer see your transient. What's h sub 1 of s look like if our pole, where's our pole? Negative 10. So this guy is now 10 over s plus 10. Our pole is at minus 10. This is now our time constant in our system. What's that look like? If I ask you to sketch that impulse response, can you? It's not too hard to sketch, is it? Where do you begin? At t equals 0. E to the 0 is 1. So this, if this is now h sub 1 of t, we start at 10 and we decay exponentially, and where are we going to draw that exponential decay? We'll be done with all that decay in 5 tau, or at half a second. So let's just say this is 0.5. This is now our 5 tau, and our let's just look at that for a while. That's a pretty good shape. That's a pretty good curve. That's h sub 1 of t. What happens in the S domain? What are we sketching over here? Think mall. Think tent. Poles and zeros. What do we have in the S-plane? We need to look at h sub 1 of s and find the poles and the zeros. Do we have any zeros? No finite values of s cause that to vanish. We do have one pole, and it's over here at minus 10. Do you see how we're now moving between the kitchen and the living room? S domain, time domain. Now what do we want to do? Suppose we excite this system with a particular input. Suppose we hit it with an input that's e to the minus 2t. What's going to happen? You're going to go home tonight and draw all of those diagrams and think about it. You can now convolve those, right? You can get x of t is a decaying exponential. H, the impulse response, is a decaying exponential. You can convolve those and figure out what y of t is. Or some of you are wanting to go quick on this, and what are you going to do? You're going to work in the kitchen. You're going to go in the frequency domain. What's a decaying exponential with a pole or e to the minus 2t? It's 1 over, or if you said 2 over s plus 2, it depends on the scaling. But now that's x of s. You can multiply it by h of s. You have y of s. You can inverse Laplace transform to get y of t and see if both sides give you the same answer. We'll pick up somewhere close to that next time.